Hi guys, Buildzoid here, and today we are going to be taking a look at the MSI Z490 Unify board. And yeah, so this is supposed to be a $300 motherboard, and basically I think this is probably the best $300 motherboard. Now, well, uh, okay, that's not entirely true, but this is certainly a candidate for best $300 Z490 motherboard. And if this actually does as well as I hope it does, then it would basically also become the best $400 Z490 board, because the significant, like, the $400 boards don't do, they don't really do anything all that special compared to this. So, yeah, let's get into it, shall we? So, starting off with the rear I/O, we've got 2.5 gig LAN, Wi-Fi 6 from Intel. I wish there was more USB ports, but MSI decided that instead they're going to have vent holes for a VRM fan. That is completely and utterly unnecessary because of the VRM this board comes with. Like, I don't get it. Like, why is there a fan on the VRM here? Like, ASRock has the Phantom Gaming Velocita, which has a fan because ASRock couldn't be bothered to design a proper VRM. This has a fan because apparently MSI ran out of stupid gimmicks to include on their motherboard. Yeah, because like the VRM here barely even needs a heatsink, and then for some reason there's a fan. And also MSI did the, the most perfect move for implementing the fan of not using a standard fan connector. So if you want to, like, I don't know, like if you actually want to connect a extra fan that's useful to the motherboard, you can't, because the hell is this? Right? Like that's the thing that I especially dislike, where it's like, so not only do we have a fan that serves literally no purpose, you can't even use the extra fan hardware on the motherboard to power a useful fan because that is the connector they went for. Like, I don't get it. Like, why? Like, and the funny thing is like EVGA, for example, has VRM fans, but you know what EVGA uses for their fan connector? A normal freaking fan connector. So any normal case fan will plug into those, and then for some reason everybody else is like, oh, we have a VRM fan. What connector are we going to use for it? Some abomination that nobody's ever seen before. Like, uh, why? Why can't, like, is this connector not good enough for you? I mean, yes, it's bigger, but come on. Um, and it's not like this area of the board like is that cramped, or you could have had it down here or anywhere really. Like, really, they could have had a second sys fan down here. That would have been fine. It would have been kind of awkward to reuse at that point, but it wouldn't really make a difference. Um, Anyway, so yeah, there's vent holes for a fan that's just completely unnecessary, but like you don't really pay any extra for it, and the board is really good in other ways. It's just kind of like, yeah, there's. I don't think if the fan wasn't there, the board would be $5 cheaper, but because it just doesn't work like that. It's just like, yeah, I'm not sure why they bothered. Anyway, we get a clear CMOS button and a BIOS flashback button, so you can update the BIOS of the motherboard without even having a CPU installed. You can also potentially use that for recovering corrupted BIOS flashes. So, yeah, moving on from the rear I/O, because quite frankly, like, this is not the worst rear I/O you could have, but it's not like, I really wish there was more USB ports. Um, well, like, yeah, and the thing is, there are other motherboards at this price point that have more USB ports. So I would have actually traded the fan for the extra USB ports. But anyway, getting down to this corner right here, this is basically the redemption for this motherboard, and in fact the main reason why I like this motherboard so much. So we've got a postcode, reset button, power button, so pretty standard overclocking features. Most of the other boards in this price range only have the postcode, but this thing gets better because it has this jumper right here. That is JOC FS1. And FS stands for failset. This is MSI's clunkier version of safe boot. Basically, as the motherboard is powering on, you hold this down, and it has to be right as it turns on. Like, you can't, like, basically there's like a couple, like, it's the very beginning of the post process. You have to short that jumper, so get your own button for it. And when you short that jumper during that short time period, right at the start of boot up, it basically tells the board to fail your OC settings and put you into the BIOS without clearing all your settings, which is really great because basically that jumper eliminates the, like, if you have a motherboard without some form of safe boot functionality like the fail set jumper or, you know, safe boot like you'd get on Asus and EVGA motherboards, the solution to bad overclocks a lot of the time is clear CMOS and load profile. Now, if you're bad at keeping track of profiles, that's not really an option, right? Like, you're going to be redoing your settings over and over again. Alternatively, there's also sometimes you run into issues with like boards not properly saving profiles, which actually the Unify has been misbehaving for me with that. Like I've had the board straight up erase all my profiles at one point. So yeah, that's not been great. But the thing is, so you know, like, but even if you're on top of saving profiles, clear CMOS load profile takes far longer to do than safe boot or fail set here does. So yeah, this is great if you're doing you know, memory overclocking and you have no idea what you're doing, or even if you have it. Like, the thing is, it just makes life so much easier if you make mistakes. So yeah, fail set like this. This is literally like the main reason I hope the rest of the motherboard is good is so that is that jumper right there. It's like that's the main thing, because that jumper is freaking awesome. Next to that, we get OCRT1, which is a retry jump, which is meant to be retry functionality. I've not managed to get that one working yet. Basically, it's supposed to be like a super reset where it forces the system to reset no matter what. You can replicate the functionality by just turning off your power supply. That also works. And the idea behind this is you can use it for really hard crashes, and you can also use it for, like, you can crash the CPU so hard the reset button stops working. And you can also use it for retraining memory. But yeah, you can also replicate that functionality with the AC power switch on your PSU. It just takes longer and is arguably less convenient. Above that, we have LN2 mode, which just loads up some LN2, like cold bug removal voltages. It doesn't actually change voltage ranges at all, which is pretty cool. And J slow, which is just slow mode, which is like a it's like it's manual power savings for LN2 overclocking is the way I use it, because basically what it does is it forces the CPU down to the lowest possible clock speed. So yeah, if you're like saving screenshots or just, you know, messing around in the OS on LN2, that's a great way to not be burned. Because the thing is, if you go from 6 gigahertz to 1.2 gigahertz, you basically cut your power consumption down to 1/5 of what it originally was, even if you don't change the voltage. And well, that reduces how much LN2 you're burning off, even if you're just sitting idle. So that is very much like, these two are very much extreme overclocking features, and I think they're a bit unnecessary on a board like this, because this is just too close in price point to the Apex, and I feel like if you're actually serious about extreme overclocking, you should just get an Apex instead. But if you're considering like if you're considering a motherboard for a daily build, at $300, like, fail set is freaking awesome to have. Even in a daily build, like, I want fail set. Like, that is such a cool that is such a cool function that, yeah, this is like every motherboard should have a postcode. Every motherboard should have a fail set or a safe boot jumper. Like, that's how much I like that functionality. Anyway, moving up, we've got troubleshooting LEDs made completely redundant by the postcode, which, incidentally, yes, the postcode is in the wrong place, and, you know, it shouldn't be under the PCIe slots. It'll get covered up by GPUs, which, especially if you're into benching, again, though, this is like nobody's actually going to seriously bench on one of these. But the thing is like, if you are testing, say, older GPUs, they run into compatibility issues when they're plugged into the CPU PCIe slots. Yeah, if you plug them down here, you're not going to see the postcode. So that's rather annoying with Z490. Like, that's actually a problem with Z490 in general, though, that like the old GPUs have terrible compatibility at this point. Like, I've not been able to boot Kepler cards on Z490, which is just like, they're not even that old. Come on. Anyway, yeah, so we have the troubleshooting LEDs up here. Then above that, we have voltage read points. These are just from the motherboard itself, so they're not like super accurate, but they're good for if you just want a rough indication where your various voltages are at. Also, these are incomplete. There's a bunch of PLL voltages for extreme overclocking that these don't include. But, and again, it's like you're not actually going to be running this board on like, I really doubt there's going to be many people running this board on LN2. I'm pretty sure MSI's own, like, in-house overclockers have run this board on LN2, but outside of that, like, I don't think anybody else is going to do it. Like, I don't want to do it. I went and bought an Apex because an Apex makes you look like you know what you're doing. Which technically the LN2 mode jumper probably manages that here as well, but it's just like, I also like not having 4 DIMM slots. So, yeah. Anyway, so this is like not really like this is a nice feature to have. I just feel like it's not going to get very frequent use on this motherboard. Also, yeah, these aren't like you're not going to get like DiSense voltage readings from that. Anyway, let's move on to, oh right, dual 8 pins. If you have a 10900K and you're hammering it, you can actually max out a single 8 pin, so you should plug in both of them. If you're on anything less than a 10900K, so 10700K, 10600K, you only need the single 8 pin. You don't need the second one. It's completely unnecessary in that scenario. So, yeah, so the dual 8 pins on the Z490 are actually reasonable. Though, honestly, an 8 pin and a 4 pin on Z490 is also perfectly reasonable, because the thing is like the 8 pin does, like each 8-pin, MSI uses the standard current variant of the connector, so these are each 384 watts. The CPU can easily pull a little bit over 400, like you can end up with a little bit more than 400 watts going into the power connectors, and it's like, well, technically just an 8 plus 4 would already give you over 600 watts of power handling capacity, so, you know, this is pretty overkill, but there's not really any problem with it. And technically, you can plug in half an 8 pin. Like I think you can plug in that part. So if you had a PSU that has an 8 plus 4 pin configuration, which is really weird. Normally, you have like either a single 8 pin or dual 8 pins. You don't normally get an 8 and a 4. But yeah. Anyway. So this actually makes sense for Z490 if you're going to be running a 10 core. If you're on an 8 core or something less than that, then you don't need the second 8 pin. So let's talk about the VRM here. And this is another thing that's really nice on this board. So this right here is the VCore VRM. And it is an absolute monstrosity, especially at $300. This is absolutely ridiculous. So this is a 8/16 phase VCore VRM. And then we have this down here, which is the VCCSA. So that's the system agent power. And both of those are controlled by this chip right over here. And there's no iGPU VRM, so the board does not support Intel QuickSync because there's no way to power the iGPU. So if you wanted to use QuickSync video encoding, well, you can't because the board doesn't support that. But there are some upsides to this. By not having an iGPU not having an iGPU phase, the VCore pins, if I'm not mistaken, are all right here. You can basically have a power plane that looks like that. Whereas if you have an iGPU if you have an iGPU phase, if I'm not mistaken, the iGPU power pins are right around there. So normally what you end up with is if you had, say, you know, this right here being iGPU, then you'd have a power plane that goes like that, and then your VCore would have to go, right? Like your VCore has to go around this right here, and so potentially, which basically just means you have more power plane impedance because any power trying to get into the CPU has to go around instead of just being able to go directly. Just being able to go directly from wherever it comes from into the, you know, power pins. So yeah, this should actually help with like transient response and power delivery efficiency a little bit. Not like power plane power losses are that high, but they're still like it's not non-existent. It is there, but it's not that much. Anyway, so that's kind of like you don't get an iGPU, you don't get iGPU functionality, but you might get slightly better, like you do get better power delivery by not having the iGPU phase, which is one of the reasons why all of the high-end Asus boards don't bother with an iGPU phase, is just like prioritize, you know, better power delivery for vCore above everything else. At the same time, it's like, I'd assume a lot of people probably, well, maybe not a lot of people, but there's definitely people who want to use QuickSync, and then it's like, but I want QuickSync and a high-end motherboard, and you can't have that with certain brands. So anyway, which, like, for some boards that makes sense, and I'd say for this board, sure. Like, I don't really have a problem with it on a board like this. There are other boards that you could get if you need the iGPU phase. Anyway, so the controller for this 16+1 VRM here is the ISL 69, well, 8+1/16+1, because the doubler's in use, but the controller's an ISL 69269. And that is running in 8+1 plus... Man, now I'm doing hearts randomly everywhere. What is up with that 8? It's not fail set. It's the legacy of the fail set jumper. Anyway, 8+1 plus 0. Like, this is a triple output controller. The +0 would normally be the iGPU phase, but yeah, this is not on this board. The +1 is, of course, the VCCSA, and the 8 is the vCore. The 8 then goes into all of these chips on the back of the board, and these are all ISL 6617s. Also, if you're looking at the back of the board going like, Buildzoid, why is it so fluffy? What did you do to this board? Well, I'll have you know I did absolutely nothing to it. These pictures aren't mine. You can tell because they have way too many pixels, and they aren't horribly blurry. Now, these pictures are from MSI. I have no idea why the motherboard is so fluffy, so don't blame me for that. It doesn't come with the fluffiness, okay? That's just this one in the picture. Anyway, so the doublers on the back of the board are ISL 6617s, and these are kind of funky because they can interleave and go from 8 phases to 16 phases, or they can be run in synchronous mode, in which case you get 8 phases, but with per channel current balancing, which is kind of like basically... The benefits to that is you get better transient response because effectively you have 2 inductors in parallel, which cuts your output inductance in half, so your current slew rate is twice as high per phase. The downside to that is your input ripple's even higher than before, but because these still current balance, you get slightly higher efficiency than if you did what Asus does, where you just take a PWM signal and jam it into 2 power stages at the same time without any kind of current balancing, and you just kind of hope that they'll sort it out themselves. So yeah, the ISL 6617s are kind of cool like that, where and they'll actually do current balancing even if they're in interleaved mode. So these are current balanced. They can double, they don't have to double, they can current balance, they also don't have to current balance, like that's also an optional functionality, but yeah, so the current balancing is normally enabled. It's the interleaving that normally gets left out in favor of better transient response. So yeah, also MSI has a hell of a lot of power plane stitching. Like it's not like it's something I've only, well, I don't normally pay that much attention to it, but this is a lot of, like, vias that they have in the power plane, which I'm not sure if that's significant, because, again, it's not something I've been paying attention to for very long. It's just kind of, like, started noticing differences in that. Like, obviously there's differences to that, but it's just, like, there's just so many things that you could pay attention to with a board that it's, like, the list would just go on forever. Right, and people already don't have, like, I already test people's attention spans with my video length as is. But anyway, yeah, so that's the control scheme here. Also, yeah, there's a lot of power plane stitching, but I'm not sure if it's more than, like, other comparable boards. In theory, having a lot more power plane stitching should just give you lower power plane impedance, which would translate to better transient response, possibly, like, better power delivery just in general. So... yeah, like that's a good thing, but it's just like I'm not sure how how you would quantify how effective it is. So anyway, that's the control scheme. So yeah, this can run 8 or 16 phases. It's probably running 8 phases with the per channel current balancing, which still means it's a bit more efficient. Also, interestingly enough, MSI has very little input filtering. Like, they just have 4 bulk capacitors for input filtering. Now, the thing is, input filtering, generally doesn't do that much. Like if you have, like I've had people message me about like having capacitor, like I think somebody had like a input filtering capacitor fall off of their GPU or something, and I literally just told them like, don't worry about it. Like it wasn't probably doing much of anything anyway. It was just kind of there, because yeah, input filtering. Like if you measure it with an oscilloscope, you'll see like big measurable differences, but I've not really noticed it having a major impact on actual like output voltage regulation performance. Which like the CPU doesn't care what happens on the 12-volt power plane. The CPU cares about what happens on vCore, and well, you can have perfectly good vCore even with god awful even if the input is rather noisy. So yeah. I'm not too like it's not really something to like. It's just kind of interesting that MSI has very few input filtering capacitors, but I don't really think it's causing it. Like I doubt it's gonna make any difference. Um, anyway, so actually, since we're already talking about transient response and capacitors and that kind of thing, what I will say, on the other hand, that I'm not very what I don't find very confidence inspiring, let's put it that way, because I don't know for a fact that this isn't going to work. It's just that this doesn't look like it should work. And that is MSI's output filtering configuration. Because basically, I'm not sure if this cap is on vCore. That one might be on VCCSA. Actually, nah, there's no way that's on VCCSA. That's gotta be vCore. Actually, we could just look at the back of the board. That should give it away. Yeah, that one's vCore. And we know it's vCore because it's right there. But anyway, so the thing is, we have basically all of this and all of this for vCore output filtering. Then we have also these extra capacitors right here. These aren't standard. Like, these are not a requirement for the LGA 1200 socket. Like, there's specifications from Intel for, like, how many capacitors you should have in the CPU socket cavity on the front of the board, not the back of the board. I think populating the back is also optional. Yeah, so MSI's decided that they're just not going to fill the back of the socket at all. It's basically empty. And the thing is just like, well, that's not confidence inspiring. Like, especially if you consider that, like, both Gigabyte and Asus are absolutely stuffing the back of their CPU sockets with capacitors. Like, Asus has managed to cram about as many 0805s as you could physically fit into the socket cavity, and Gigabyte is jamming freaking 470 microfarad tantalums into the socket onto the back of the socket. And then there's MSI, where on the Unify they've just kind of gone like, yeah, we don't need capacitors. And the thing is, yeah, this just doesn't look like that's going to be great for transient response. At the same time, this seems to be like the fact that these are here, but the actual, like, the back of the socket itself is empty, seems to confirm my suspicion that because the thing is, all of the capacitors you have on the back of the board, they need to go through the vias of the PCB to get to the actual to the pins of the CPU socket, because the pins are SMT. They don't go through the board, so they only connect to the very top layer of the motherboard. So essentially, like these caps right here, those are on the same layer as the actual pins of the CPU socket, but the ones on the back of the board aren't. So like, I've had a sneaking suspicion that the back of the board capacitors aren't actually that, like, they're not necessarily that effective, because they have a bunch of impedance between them and the actual CPU socket itself, which would explain why MSI kept these but emptied the back of the board. And then the front of the board, like, this is actually, like, the socket itself is full. Like, we can't see it, but they didn't, like, empty out the actual cavity, like, the front side of the CPU socket. So this is still full. It's just I don't have a picture of it. But the thing is so we have regular through-hole aluminum polymer bulk capacitors. We don't have that many multi-layer ceramics. The multi-layer ceramics that we do have aren't really that big. These are just 0603s. Another thing that I notice is the actual bulk caps are relatively far away from the socket, as in this distance right here is quite large. You'll notice that, say, like Asus especially, or well, ASRock does it as well, but Asus and ASRock will have basically capacitors going like this to the CPU socket. And I do think that's actually effective, but I've not been able to prove it. But I suspect that's effective because I tested a Gigabyte ITX board, which just absolutely just beat every other Gigabyte Z3, like for Z300 series boards. The best transient response board I tested from Gigabyte was a little overheating prone 6-phase ITX board, but that board just happens to have the entire bulk, like most of the bulk capacitance jammed right up against the socket, whereas even something like the Z370 SOC-LN2 board, which is a true 8-phase, so also no doublers, same as the ITX, yeah, that one has the capacitors quite a bit further away and loses to the ITX on transient response. So I kind of suspect like basically what I'm trying to get at is yeah, this right here with where these capacitors are located and how many of them there are is like, this is probably not going to be the best regulated board out there. Now, that doesn't necessarily mean it's going to have horrible undershoot, but I'd be very surprised if it did very well on overshoot, because and overshoot ultimately doesn't matter that much, but overshoot is kind of the easy metric to just brute force with capacitance, because basically you get low VR, like you get low overshoot by just having enough capacitance to store the excess energy from the inductors when the CPU decides that it doesn't need it anymore. Whereas for undershoot, you just need to have, like, you basically need to have a lot of very low impedance capacitance available so that the CPU can suck power out of the capacitor banks while the VRM desperately tries to catch up with whatever the CPU is doing. This doesn't, like, this looks like it might be able to deal with, like, depending on how the firmware is set up, this probably won't have that much of an undershoot problem, maybe. But I really doubt it's going to do well on overshoot. Like, this just doesn't look like there's enough capacitance to do a good job on overshoot. So, yeah, basically my main concern with this board, and I hope I'm wrong about this, is the transient response. So ultimately, we need to ask the oscilloscope about that, because I can't eyeball this. There's too many variables. It's like, how's the power plane designed? How are the capacitors, like, what capacitors are in use? Where are the capacitors? How are the capacitors connected to the power planes? How is the voltage controller firmware configured? You know, like, too many variables. So, but at the same time, this is not confidence inspiring. So, yeah. Anyway, moving on to the actual power handling capacity itself, that is very confidence inspiring because, yeah, we've got a hell of a lot of phases, or at least a hell of a lot of power stages, depending on how the doublers are running. And then the power stages are ISL 99390s. These are 90 amp smart power stages. Now, the 90 amp figure is a bit misleading because the thing is, there's a pretty hard limit for how efficient a power stage can be, and the 70 amp smart power stages already basically hit that limit, and then when you get to the 90s, it doesn't really change. They are ever so slightly more efficient, but ever so slightly. So I find, like, personally, if a motherboard has 70 amp smart power stages or 90 amp power stages, I consider them to be the same thing. They are, as far as I'm concerned, equivalent, because the 90s, well, the funny thing is the 90s actually have their performance graphs ending at the exact same current figures as the 70s. Like, nobody actually specs their high current power stages past 60 amps because, like, even if your power stage is doing 90% efficiency, if you're pushing 90 amps at let's say 1 volt, if you're outputting 90 amps at 1 volt and you have 90% efficiency, you're going to be producing 9 watts of heat per power stage. Like, that is not a practical amount of heat to be producing per component in a multi-phase VRM. Sure, if you have one power stage, you can deal with 9 watts of heat. If you have like 3 of them, that's 27 watts of heat. Like, no, you're gonna need an absolutely stupid heatsink for that. So yeah, it's just like the 90 amp figure is like, it looks really good in marketing. It's not actually useful. Like, it's basically like 90 amp smart power stages are basically the same thing as 70 amp smart power stages, which aren't even that much better than like the 60 amp smart power stages, which is kind of funny as well. But then once you go below 60, it actually starts being drastic differences for every 10 amps. Like 60s versus 50s, major big difference. 50s versus 40s, massive difference. 40s versus 45 versus like 35s, also a massive difference. So, yeah, that's kind of the funny thing with the current ratings is just kind of like these are like they're not a real world figure. Like you could actually push 90 amps through one of these power stages under very specific operating conditions. Practically speaking, not a useful number. Anyway, but they are still, 90 amp smart power stages and therefore ridiculously efficient. And also these are called smart power stages because they integrate more accurate current monitoring, temperature monitoring, and a bunch of safety features like overcurrent protection, over temperature protection. And I think they even have like short circuit protection and like a bunch of advanced safety features that normally you'd have to, well, actually, if you have a really dumb, like if you have a DR-MOS component, you have to implement your own current sensing circuitry. With these, that's built into them, so you don't have to worry about that. So that's why these are called smart power stages. They basically include a bunch of functionality that otherwise with like more basic power stages you would have to add yourself with external circuitry. But these eliminate that, and in some cases they actually do it better than if you were doing it externally. So yeah, anyway, let's talk about the VRM efficiency here. So 1.2 volts output, 500 kilohertz switching, that's a terrible 500 kilohertz switching frequency. This VRM is going to do 200 amps while producing 15 watts of heat, which is literally less than 1 watt per component. It's also outside the peak of the efficiency curve. Like, depending on how the controller is configured, it shouldn't be running all 16 power stages if you're only doing 200 amps. Like, it should honestly probably drop off like this right here. Like, it should just not run that, or this down here, in order to get into peak efficiency, because power stage efficiency curves look like this, where at very low currents, the efficiency is absolutely atrocious, and then there's an efficiency peak at some point, and then anything, like, if your current is too low, your efficiency is bad. If your current is too high, your efficiency is worse. So, yeah, anyway. So this is actually before the efficiency peak. Then 300 amps output, this VRM is going to be producing, but this is so little heat that you literally don't need a heatsink. At less than 1 watt per component, yeah, you don't need a heatsink. Like, the VRM is going to cool itself by the nature of just having so many power stages. 300 amps output, it's going to be producing about 23 watts of heat, and even at 300 amps output, you don't really need a heatsink, because, again, this is barely above a watt per power stage, and they can still dissipate that on their own. Though at this point, it starts also depending on, like, whether or not you need the heatsink starts depending on the ambient temperature as well, because, like, I've done tests with this type of VRM in a 20-degree room, and it would sit around 90, like, it would end up at around 90 degrees, which is perfectly fine for power stages. Now, the thing is, of course, if the room was 50 degrees, then it would be at like 120 degrees on the VRM, which is not so great anymore. Not that the power stages would care about it, but like the capacitors would. Those are only like those are rated for 10,000 hours at 105 degrees. All of them are made by Nippon Chemicon. So they're nice high-end capacitors, but it's still like if you want their full, like, the thing is, the cooler you run the caps, the longer they last. So, and like the lifespans are significantly more temperature sensitive than the actual power stages. So, yeah, that's kind of the thing there. Anyway, 400 amps. So 300 amps, depending on just how high the ambient air temperature is, you might actually need a heatsink. 400 amps, the heatsink is no longer negotiable, but the other thing is you're not going to hit 400 amps unless you're doing extreme overclocking, because 300 amps on a 10900K is doable. It's very, very demanding on your cooling system. Like, you're going to need one hell of a cooling system to push 300 amps into a 10900K. And so for most people, you're going to run out of, like your cooling system's going to, your CPU cooling is going to be inadequate before the VRM stops being adequate. At 400 amps, well, you're not going to be doing 400 amps unless you're sub-zero. And I don't think, like, again, I don't think many people will be taking this board sub-zero, but if you did, well, the other thing is if you're sub-zero, you don't run Prime 95 for several hours. So it's like not really, or you're not going to do like a multi-hour 3D render of something. So you're still not going to overheat the VRM by nature of the test being too short to do that. But anyway, 500 amps output. VRM is going to produce 48 watts of heat. Basically, what I'm trying to get at is this is like a HEDT grade VRM on a mainstream platform, but that's not really that special because the funny thing about like mainstream motherboards is because they don't have DIMM slots on both sides of the CPU socket. The motherboard vendors have the freedom to build a lot of VRM very easily because don't need to really get very creative with the layout. Like if this wasn't here, there's just a bunch of empty space, right? There's nothing else to put in that area of the board. Anyway, 600 amps output, the VRM would produce about 66 watts of heat. So, yeah, this is just absolutely, like, you're not going to get a more powerful VRM at $300 than this. In fact, even the $400 boards are basically like you're actually like this is as powerful as you're going to get a VRM on Z490. So then the only question is, how is the voltage regulation, right? And I've already shared my thoughts on that. Like the capacitor configuration here is not confidence inspiring, but well, it's not going to overheat. That's definitely not going to be an issue. So then it's just a matter of like, but how much V-droop will you have to run? Because the funny thing is, assuming the VRM controller firmware is set up correctly, if you just give the VRM enough V-droop, you're not really going to have a voltage regulation problem either. So, yeah, but that's the efficiency situation. Like that's the power delivery situation for VCore. VCCSA we have just two discrete MOSFETs, high side, low. Actually, I think I have those backwards. It doesn't matter which one's which. Either way, we just have two discrete MOSFETs, and those are a 4C029N from On Semiconductor, as well as a 4C024N. And I just realized that my 9 and my 4 are going to look the same. Yeah, see? There, that's a 4. And these are actually really nice discrete MOSFETs. Like, these are better than what you get on a lot of low-end motherboards for your VCore, which is depressing. The low-end motherboards are not this. This is cool. But VCCSA is not a high current rail, so this is perfectly fine. In fact, this is more than fine. And plus, it gets to share the massive VRM heatsink that, is here for the VCore VRM that's not actually going to be using it. So this is going to have more than enough cooling, even though, like, VCCSA isn't a high-power rail either. So, yeah, like, basically VRM, like, power handling capacity here is plentiful. So, yeah, interestingly enough, VCCSA has a lot of multi-layer ceramics on it. Funny how that works. Anyway, then we've got all of these voltage regulators down here for the various minor rails like the PLLs and VCCIO, so, various voltages for extreme overclocking. Then for the memory power, we've got this right here, which MSI's finally stopped doing the 4 MOSFET memory VRM. So now we just get 3 MOSFETs, which is still more than enough. The thing is, DDR4, it doesn't pull a lot of power, and it's also not really about, like, you also, like, this is just a single-phase VDDR, but memory is very much not about how you power it. It's far more about how you connect it to the actual CPU, right? So, and we'll get to that, but anyway, so for the memory VRM, single phase, and the MOSFETs are a 4C029N high side, and then 2 4C024Ns for the low sides. So that's these two right here. Anyway, for the actual memory topology, the motherboard is a 6-layer PCB, which technically the layer count is kind of relevant to also like the power plane impedance and a bunch of other things, but yeah, like it's easy, like it's easiest to mention in the memory section. So anyway, 6-layer PCB, MSI is using the tabbed memory traces, so that's this stuff, which basically what they're doing is you have, if we actually draw out a couple, actually, I should just have a more close-up picture of this, but basically the idea is you have these tabs on the memory traces, and by some form of electronics engineering magic, that reduces crosstalk between the memory traces. And crosstalk is basically interference between the signals running down the traces. Yeah, so that's what MSI is doing with their memory topology. I don't think anyone else is doing this for Z490, or at least I've not noticed it on any other boards. Whereas MSI at least has it extremely obvious, because like this just doesn't look like any memory traces you've ever seen before, which is why I noticed it. Yeah, so we have a tabbed daisy chain topology here, and as for how well does it work, well, I've actually been testing the Unify, and it works really well. And I don't know why I capitalized daisy chain and not the tabbed. I'm awesome, aren't I? Anyway, so MSI claims support up to 4800 megahertz on 1 rank and 1 rank. So obviously it's a daisy chain, so it favors these two DIMM slots. And I can confirm that 4800 is very much possible. It's not fun for your memory controller. It requires absolutely stupid amounts of ECCSA, and I would not try to daily 4800. Like, maybe on a 2-DIMM board it might not be so difficult to run, but on a 4-DIMM, and I just stabbed the mic with the stylus, sorry about that. Yeah, at like 4800 on this board, just like you can do it. You can take screenshots of it. You can run benchmarks with it. In fact, you can probably pass memtest with it. I've not managed that yet, but like I gave it a try, and it just like it's like it's very difficult. I think I probably need to use Hynix DJR, because as far as like, so BDI is just BDI, so it's really heavy on the memory controller. Micron Rev E seems to have a really hard time with Intel, like, or more like Intel memory controllers seem to really hate Micron for whatever reason. Like I can't get it to clock, like be stable. Like I can get it to clock plenty high, but getting it stable is a nightmare. And actually it clocks worse on Z490 for me than on X570. So the kit I did 5.1 gigahertz memory clock on, yeah, I can't do like I've not managed to do 5G with it on Z490 yet. Anyway, so BDI at 4800 is hell for the memory controller. Rev E does 4800, it's just not very stable, and I don't currently have any Hynix DJR, but I'd assume with Hynix DJR this should actually be, like, viable, but Hynix DJR is also significantly slower than BDI, so I don't know why you'd be bothering to run that anyway. Yeah, so 4800 technically doable. So the motherboard's memory topology is capable. It's just kind of like the other parts of that equation don't really work that well. Now, what's really interesting is that if you run 1 rank in every single DIMM slot, which is theoretically suboptimal for daisy chains, it actually runs really well. The board can go all the way up to 4400. Optimally, you should really be going for like 4266 or 4300 if you actually want good timings, because at 4400 you start having some like some of the timings start being like requiring to be really loose, and that hurts overall performance. But yeah, like at 4300 you can run, 4x8 at very tight timings, and the performance is absolutely amazing. So if I was actually doing like a daily system with this board, so like 10900K or even 10600, well, 10600K is kind of silly to pair with a board like this, but regardless of what CPU you stick into this board, I would probably go for 4x8 memory configurations, just because for daily usage, that actually works really well. So, yeah. Now, interestingly enough, 2 ranks on just the 2 favored DIMM slots doesn't actually work that well. That only is support, like MSI only claims support up to 4266, and that is in line with my own results in testing, which is still actually quite good, because 2 rank memory sticks tend to have god-awful support on most motherboards. So yeah, like this is actually still impressive. It's just kind of like you should actually just be running 4x8 anyway instead of trying to mess with like 2x16. Though these days you can actually get single rank 2x16 kits and well, you might be able to run high frequencies with it. It's just probably going to be slower than 4x8 dual rank, right? Like it's still going to be slower than this because that has dual rank performance benefits. Um, anyway, and finally, if you're going for high capacity, MSI claims support for 4000, and I've not tested that at all. I have no idea if it works well or if it works at all, but considering that all of the other speeds have been basically in line with my experience with the board, I'd assume that the 4000 works just fine as well. So, yeah. MSI's like I'm actually really impressed with what MSI has done for their memory topology. It works really well, at least in like 2x8 and 4x8 configurations, and even 2x16 works quite well. So, yeah. As far as so basically with the Unify, the only question I have at this point is like, how is the transient response? Because power handling capacity is great. Memory overclocking is very capable. We've got a postcode. We've got fail set. The rear I/O could like it's not incredible, but it could be worse. Well, the rear I/O is basically as complete as I would like it to be. And yeah, like there's very little that this motherboard doesn't do. So it's now just basically the only thing that I'm wondering about at this point is like, so how does that reduced capacitor configuration work out? Because if that still does good on the undershoot, then it's like, why would you buy anything else? Right? Like that's kind of how I'm looking at this board at this point, where it's just like, there's really no reason to consider any other motherboard in my opinion, because it's like great current handling capacity, great feature set in my opinion. Like, what more could you want? So, yeah, like the Unify is kind of the problem. Like, it could end up being the best. Like, well, not necessarily bank. Well, I don't know. Like, for like the thing is, it's also just $300. So, like, I consider this one of the most interesting Z490 motherboards. Like, the main issue I have right now is just, like, I have no idea how it does in terms of transient response. So, yeah, and that would basically mean, like, if the transient response is bad, it could be like, well, if you have a CPU that does 5 gigahertz at, I don't know, 1.3 volts load voltage on some other motherboard, then on this board it might have to run 1.32 volts, right? Which is like, or 1.33 volts, which isn't necessarily that big a deal, but it does mean the CPU runs hotter, and, you know, like, it would be better if you didn't need the extra voltage. And there are other motherboards at $300 which, technically speaking, have like more USB ports in the rear I/O. They still have the postcode. They don't have failset, which is like that. They don't have failset, right? So it's like, would I be willing to trade failset for 10 millivolts better voltage regulation? Nah. No, I wouldn't. I would rather have failset than better transient response. Would I trade it for 20 millivolts? That's a more difficult question. Would I trade it for 30? Probably. For 30 millivolts, I think I'd probably trade it. But, because 30 millivolts is, like, significantly more heat output. But, yeah, if, yeah. So we'll have to see. But basically, hardware, like, from what I can see on the PCB, this is a really, really cool motherboard. And even so far from some of my own testing experience with this board, is like, this is definitely a candidate for being one of the best Z490 motherboards out there. So, yeah, it was just like, I just don't want to give it a recommendation, because this just, like, the thing is, I still wouldn't be able to give it a recommendation even if they hadn't left out all of the capacitors, because there's plenty of boards where the capacitor configuration looks fine, and then you test it and it's like, well, this doesn't actually work that well, does it? Yeah, but that's the Z490 Unify. So I just hope it really works out. Like, basically, I can't wait to get the oscilloscope measurements for this board because I'd love to basically be this board does so many things so right, and then it's just like there's just one last question to answer, in my opinion. So, yeah, that is it for the video. Thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon where you can support me directly. So there's a link to that down in the description below. And then there's also the AHOC Teespring store where you can pick up shirts, stickers, posters, you know, the usual YouTuber merch, which achieves exactly the same thing as the Patreon, except you get merch in return. So yeah, you help out the channel and you also get stuff. So yeah, that's it for the video. Thanks for watching and goodbye.